In this video, I will talk about the fundamentals of neutron diffusion equation first, then demonstrate how to solve the two-dimensional one-energy group neutron diffusion equation using MATLAB PDE Toolbox. Before I go to the neutron diffusion equation, let us first study the neutron flux and the cross-section. If you want to know more about those reactor physics concepts, please go to the 4397 course. The neutron flux is the unknown we are trying to solve, just like the temperature we were solving when dealing with the heat transfer equation. So after solving the neutron diffusion equation, we will get the neutron flux distribution on the 2D domain. The neutron flux is a measure of the intensity of the neutron radiation. It is defined as the N times the V. The N is the number of neutrons per cube centimeter, which is the neutron density, and the V is the average neutron velocity. So the N times V will give you the flux unit, that is number of neutrons per square centimeter per second. Again, the neutron flux is the unknown we are trying to solve. Next, we will talk about the cross-section. We can consider the cross-section to be the material property we need to enter to define the property of those material inside the reactor. We have two types of the cross-section. One is microscopic cross-section, another one is macroscopic cross-section. The microscopic cross-section is the property of the atomic nucleus. So that is the property of one single atoms. We use the lowercase sigma to represent the microscopic cross-section. It is a measure of the possibility of the reaction between the incoming neutron and the target atomic nucleus. If this value is high, it means that it is relatively easy for the neutron to react with this atomic nucleus. This value depends on neutron energy, type of material, and also the material temperature. And the unit for this microscopic cross-section is square centimeter. When solving the neutron diffusion equation, however, we will not directly use the microscopic cross-section. Instead, we are using the macroscopic cross-section. The macroscopic cross-section is the property of the actual material inside the reactor. We use the capital sigma to represent the macroscopic cross-section. The macroscopic cross-section is equal to the capital N times the macroscopic cross-section. This capital N is the atomic density of this material. So this macroscopic cross-section depends on not only the property of the atomic nucleus, but also the density of this material. And the unit for macroscopic cross-section is 1/centimeter. There are different types of cross-sections for representing different reactions. For example, we have absorption cross-section, neutron is absorbed by the target material, and also the scattering cross-section and also the fission cross-section, which represent the reaction possibility to trigger the fission reaction. In addition, another variable often associated with the fission cross-section is the mu, which is the average neutron released per fission reaction. In this course, the macroscopic cross-section will be given by the problem as part of the material property. The next concept is the reaction rate. The reaction rate is the number of reactions per unit volume per second. The reaction rate is represented by the capital letter R, and it is calculated as macroscopic cross-section times the neutron flux. And the unit for the reaction rate is the number of reactions per cube centimeter per second. For example, if the macroscopic cross-section is the fission cross-section, then we can calculate the fission reaction rate, RF. This RF is equal to the macroscopic cross-section for the fission, then times the neutron flux. This fission reaction rate is important because the reactor thermal power is proportional to the fission reaction rate. If you have more fission reactions, then you will get higher power because each fission reaction will release certain amount of energy. Next, let's introduce the neutron diffusion equation. The neutron diffusion equation described the basic neutron balance. So the basic neutron balance is that the rate of neutron change is equal to the production rate minus neutron loss rate. Or mathematically, we can say that the rate of change is dN over dt is equal to the neutron production rate from the fission reaction minus the neutron loss rate. The neutron loss include two parts. One is neutron absorption by the reactor material. Another one is neutron leakage. So if the neutron travel out of the reactor, then those neutrons will be deleted from the system. In this course, we are going to study the steady state condition. For steady state condition, the rate of change will be equal to 0. So our left-hand side will be 0. For the first step, we will study the one group or one energy group neutron diffusion equation. In that case, we are going to treat all the neutrons as a single energy. So often we can also say that it is one speed steady state neutron diffusion equation. And the one group neutron diffusion equation is written in this blue equation. So that is negative gradient D gradient flux plus sigma A times phi is equal to mu sigma F over K times the phi. The first term is the leakage term. The second term represents the absorption, and the last term on the right-hand side represents the fission. In this equation, the capital letter D is the diffusion equation, is the diffusion constant. The phi is neutron flux. Sigma A is the macroscopic cross-section for absorption, and sigma F is the fission macroscopic cross-section. K is called the multiplication factor, and this mu is the number of neutrons released per fission. Now let's talk about the K. So the K is called the multiplication factor. This K is also an unknown, and we have to determine its value after the calculation. The K is the neutron production rate over the neutron loss rate. So if the neutron production is higher than neutron loss, then you have more and more neutrons over the time. And if this neutron production rate is lower than the neutron loss rate, then your neutron population is going to decrease. Therefore, this K will give you the criticality condition of this reactor. If the K is higher than 1, the reactor is supercritical, and the power is increasing because you have more neutrons, and more neutron is going to trigger more efficiency, and eventually you have more power. If the K is equal to 1, then this reactor, we can say it is just critical. Then the reactor power is stable. And if the K is smaller than 1, we call that this reactor is subcritical, and the reactor power is going to decrease. If you do not fully understand the meaning of this neutron diffusion equation, that is fine. You can just treat this equation as a regular differential equation. Okay. Next, let's talk about the MATLAB PDE toolbox. The MATLAB PDE toolbox contains two different workflows. One is based on this graphic user interface we are going to study in this course. The MATLAB PDE modeler, which is the GUI, can model a generic scalar eigenvalue problem. And the general equation the MATLAB PDE modeler is going to solve is listed here. We can compare these two blue equations. So this generic equation in the MATLAB menu and also our neutron diffusion equation. We can see that the unknown U is just the phi, that is neutron flux, and the C is just the D, which is our diffusion coefficient, and the A is the macroscopic absorption cross-section, sigma A, and the D is mu sigma F. The lambda is called the eigenvalue, and compare these two equations, we can see that the lambda is equal to 1 over K. Therefore, we just mapped our neutron diffusion equation to the MATLAB equation. So if we enter those values properly, we can use this MATLAB PDE modeler to solve our problem. The graphic user interface can solve one speed or one group neutron diffusion equation, and also the two group neutron diffusion equation. And if we are trying to solve the neutron diffusion equation with more energy groups, we have to use the more advanced workflow, which is purely based on the script. And the script workflow is not covered in this course, and we will just study the MATLAB PDE modeler based on the graphic user interface. And we will solve the one group and also the two groups neutron diffusion equation later. From our previous study, we know that to solve a differential equation, we also need to define the boundary condition. The neutron diffusion equation can take 4 different boundary conditions. When we are studying the one group neutron diffusion equation, we are going to study the first 3. At a later time, we are going to study the 4th type of the boundary condition. The first type of the boundary condition is called the zero flux boundary condition. For zero flux boundary condition is simple. We simply set the neutron flux to be 0 at the core boundary. It is similar to the temperature fixed temperature boundary condition when we were solving the heat transfer equation. So we simply set this unknown phi to be 0 at the on the edges. Therefore, we are going to use the Dirac-Lett boundary condition, Dirac-Lett type boundary condition. And the Dirac-Lett boundary condition equation is H times U is equal to R. So U is our phi. Therefore, to make this phi equal to 0, we are going to set the H to be 1 and the R to be 0. On this slide, the red font are the values you are going to enter to the PDE toolbox. Okay, so the red color are important. The second one is called the vacuum boundary condition. It means that the neutron can leave those boundary, but they do not come back. It means that it describes a condition that the core, outside this core, it is vacuum, and there's no other material that can reflect the neutron back to the reactor. So this vacuum boundary condition is more realistic boundary condition than the zero flux boundary condition at the core edge, because realistic at the core boundary, the neutron flux is not zero. It's low, but not zero. So for vacuum boundary condition, the neutron current on the boundary meets the following condition. So 1 over phi d phi over dn is equal to negative 1 over d. So this n is the vector normal to the boundary. This d is the extrapolation distance. So the d is called the extrapolation distance, and it is equal to 0.7104 times the lambda tr. That is the mean free path. Then lambda tr is equal to 3 times d. So this d is our diffusion coefficient. Then we can rearrange the above equation, and we get this blue equation. So that's d times d phi over dn plus capital D over lowercase d, then times phi is equal to 0. Then in the second term, the diffusion coefficient will be cancelled. So we get this black equation to the right. This one describes the current, which is the first derivative of our unknown. Therefore, we are going to map this equation to the Newman boundary condition. In MATLAB, the Newman boundary condition, the equation is written as C gradient U plus Q times U is equal to G. Then compare this blue equation with our vacuum boundary condition equation. We will see that the C is equal to the D, which was previously determined when we are mapping our differential equation. So we don't have to worry about the C. Then U is our unknown, which is the phi. The Q is equal to the D over lowercase d. So the Q is equal to 1 over 0.7104 times 3. So it's equal to 0.46922. And the G will be equal to 0. So when you are setting the vacuum boundary condition, you just simply choose the Newman boundary condition type and set the Q equal to 0.46922 and G is equal to 0. The third type of this boundary condition is called the mirror boundary condition or reflective boundary condition. This one is similar to the insulated boundary condition when we were solving the heat transfer equation. This one simply describes the neutron current to be 0 on certain edge. For example, at the center of this core, if the core is symmetric, then along this symmetric axis, it is a mirror boundary condition. And neutron current J is equal to negative D times d phi over dn, and it is equal to 0. Again, this one describes the neutron current. So we use the Newman boundary condition. Then compare the Newman boundary condition MATLAB equation with this 0 current equation. We can see that both Q and the G are 0. Therefore, when you are setting the Newman boundary condition, when you are setting the mirror boundary condition, simply choose the Newman type and set the Q and G to both 0. Let us use one example to demonstrate how to solve this one-group two-dimensional neutron diffusion equation. So this problem comes from the Stacy's textbook as one of the homework problem. The original problem does not include this figure, so I just draw this figure for you. However, it is your responsibility to construct this core model based on the description. So the problem is that calculate numerically the effective multiplication constant, that is the k, and the flux distribution, that is our phi, in a reactor with rectangular cross-section, which is sufficiently tall that XLZ leakage can be neglected. So it means that this is a 2D problem because Z is infinite long, where the reactor is extremely tall. The core cross-section in the XY plane consists of 4 symmetric quadrants. The upper right quadrant consists of core region 1, rectangular. X is between 0 and 50. Okay, X is between 0 and 50. Y is between 60 and 100. So it means that the X is 50 centimeters wide and Y is 40 centimeters tall. So core region 2, X is also rectangular shape. X is between 0 and 50, Y is between 0 and 60. And we also have a reflector region. 3 is also rectangular. So X is between 50 and 100 centimeter, Y is between 0 and 100 centimeter. The nuclear parameters are listed in this table. So you have the diffusion coefficient, you have the sigma A, you also have the mu sigma F, okay, for 3 different regions. And this core contains 4 quadrants, and we are going to take the advantage of the symmetry. Therefore, we will just model the first quadrant as shown in this figure. Okay, as shown in this figure. When we are modeling this figure, modeling the model in this figure, we need to apply the vacuum boundary condition to the top edge and the right edge. And we need to apply the mirror boundary condition to the left edge and also the bottom edge. Besides that, we also need to plot the x direction flux distribution at y is equal to 30 and also equal to 80 centimeter. So this is the problem. We need to solve this model and calculate the k and the flux distribution, and also determine the flux profile along 2 lines. Okay, y is equal to 30, that is at the center of the core 2. Y is equal to 80, that is at the center of the core 1. Okay. Now let's go to the MATLAB and demonstrate how to solve this problem. The MATLAB to demonstrate how to solve this one-group two-dimensional neutron diffusion problem. I'm using MATLAB 2019A with update 7. First, I'm going to launch the PDE Toolbox. Okay. Go to App, PDE Modeler. and choose the generic scalar by default, and I'm going to turn on the grid. First, I'm going to draw the core 1, core 2, and reflector. I will set my origin at the lower left corner of this figure. So I'm going to draw the core 2 first. Okay. So the left is 0 and the bottom is 0. So the width is 50. Height is 50. Height is 60. So we call this one as core 2. Click OK. And it is very big, so I'm going to change the axis limit until 100. From 0 to 100, or negative 10 to 110. Negative 10 to 110. Okay. Now draw the core 1. Double click to set the coordinate and the dimension. So here the x minimum is 0, and the bottom is 60, width is 50, height is 40, name is core 1. Okay. Next, draw the reflector. 50 centimeter wide, 100 centimeter tall. Reflector, and click OK. So this is our geometry. So we can press Command A. So I'm using a Mac, so I'm pressing Command A. On Windows, you press Control A to select everything and show the boundary. Yeah. And we don't have to change the set formula because it is just the unit. Next, I'm going to save this one. Save this one as Neutron Diffusion Example 1 model. Okay, save it. And let's go to the PDE mode. Select the menu PDE mode. You can also show the subdomain label, so you confirm you have 3 zones that will meet our expectation. So the core 1 is this one. Okay, this is our core 1. Double click this one. Choose the eigen mode. Enter the C as our D, which is 0.65. Enter the A as our sigma A, which is 0.12. Enter the D as our mu sigma F, 0.1825. Okay. Double click core region 2, core 2. So the C is 0.75, that is the D. Sigma A is 0.1. Mu sigma F that is 0.15. Click OK. In the reflector region, C is 1.15. Sigma A 0.01. D, that is 0. Press OK. This will finish the PDE coefficient. Next, we go to the boundary mode. We can click this partial omega. So let's first set the mirror boundary condition, which is 0, which is all 0 and simple. So hold your shift key and select these 4 edges. Okay, these 4 edges. Double click anything, any of the edge you selected. Choose Newman, and the default is all 0. So click OK. Okay. If it is Newman, then it is set to be blue. If it is direct light, it will be red. Okay. For example, default this one is direct light, and we select all the top and right boundary condition boundaries. Double click. So for the top and right boundaries, they are vacuum boundary condition. So for the vacuum, it's still Newman. G is 0. Q is 0.46922. Okay, click OK. Next, we go to the mesh mode. Okay. By default, it will give you some mesh. And from now on, we are going to change the mesh parameter. Okay, change the mesh parameter. So here, you enter some value not too small at the beginning. Okay, we try 5. So this is our maximum edge size. Click OK, and click this button. It will generate the mesh. Okay. Looks like the mesh is relatively coarse. Okay. So we can turn on the axis equal. Okay, so it will be a square. And we are going to further reduce this to 2. Click OK. Okay, generate again. Now the mesh looks good. Okay. Next, we will change the parameter, solving parameter. Okay, click solve, then parameter. And by default, you see that the eigenvalue search range is from 0 to 100. That is too big. And here, we are going to try from 0 to 2 first. Okay, from 0 to 2 first. Because we know that the multiplication factor k, or from 0 to 1 first. Multiplication factor is a value that is around 1. Okay, that is around 1. And if the k is larger than 1, then our lambda will be smaller than 1. So we try from 0 to 1 first. If nothing is found, then we will further expand this this search range. Okay. Do not use a very large search range, otherwise your calculation will not finish within short period of time. Okay. We try from 0 to 1 first. And the first one must start from 0, because we want to find the lowest lambda. Okay, therefore the first one must be from 0. And the second value can be any small value. Okay, but do not use a very large value. Okay, from 0 to 1 will be a very good first try. Okay, and click OK. Then you can click this equal sign and solve it. On the background, you will see that there are many many calculation being done. Now the solution has been found. We are going to adjust our plot. Okay, click this button. Okay, click this button, and I prefer the jet. Okay, prefer the jet. Plot again. Okay, now looks better, more colorful. And you see that here I have the all negative neutron flux. Okay, all negative neutron flux. This is not realistic because neutron flux should be all positive. Okay, but this solution is correct. Okay, solution is correct because the neutron flux phi appear in all the terms inside the neutron diffusion equation. So if the phi is a solution, then negative phi is also the solution. Therefore, it is possible for the solver to return all negative solution. Okay, just how the solver depend on how the solver work. And we are going to manually change all the values to be positive. So here you see the property by default it is U. Okay, by default it's U. And we are going to click that and choose the user entry. Okay, choose the user entry. Now here you can enter the variable you want to plot because I want all the U to be positive. So simply I'm going to type negative U, then plot again. Okay. This time we will have all the positive phi. Okay. So you have your highest neutron flux at the core, at the center of this reactor, and you have a lower value around those boundary. So this will meet our expectation. Okay. Another thing is that here you can choose different eigenvalues. Okay, you can choose different eigenvalues. So in this problem, we have found tens of eigenvalues. By default, it will automatically select the lowest one. So this is the one we want. So we don't have to change anything here. Okay. Next, we are going to click the height. Okay, click the height. And again, it will be user entry negative U and plot. Okay, now we have a 3D figure. Okay, 3D beautiful figure. We are going to keep this figure floating. Okay, do not close this one. We just put it to another location, put it away, and close this one. Now we are going to export the solution. Okay, export the solution. When you export the solution, you will see that here you have two variables. One is the U, that is the eigenvector, which is neutron flux. Another one is the L, that is your eigenvalues. Okay, let's click OK. You will see that in your MATLAB workspace, you have both U and also the L. Okay. And next, we are going to export the meshes. Okay, we have PET. Okay, click OK. Look at here, you have a PET export. Then we can close this one and go back to our MATLAB main window. Now I'm going to get a new script. Okay, new script here, and save it. We will call this one as model and plot. Okay, let's save. First, we are going to display our eigenvalue. Okay, display our eigenvalue. So we simply disp k is equal to number to string 1 over L1. Okay. This one means that you see that here for this eigenvalue, let's double click this one. It has 33 entries. It means that between 0 and 1, it found 33 eigenvalues. We only need the first one. Okay, we only need the first one. Therefore, here I'm going to type as L1. Okay, type L1, and we run it. You see that k is equal to 1.4961. Okay, this is what we want. Next, we are going to do a plot. Okay, do a plot. First, we type hold on. Means that the additional plot will be overlap the existing plot shown here. Okay, shown here. And I'm going to turn on the grid. Okay, turn on the grid. And I'm going to have my x label. That is x centimeter. Okay, x centimeter. Y is also centimeter. Z will be neutron flux. Okay, Z is neutron flux. Here, the neutron flux has no unit, because by solving this neutron diffusion equation alone, we will not be able to get the actual neutron flux value. To get the actual neutron flux value, we need to know the reactor total power or the reactor power within a certain region. The reason is that if the phi is the solution, then the phi multiplied another scalar value, it will also be the solution to the system. So different students can get a different result. But the neutron flux shapes and also the k should be the same. Later, when we are studying the two-dimensional problem, we will learn how to normalize our neutron flux so that all the students will get the same result. And here I'm going to show two different methods that will plot the flux distribution along a line. Now we already have this two-dimensional flux distribution. Next, we will just plot these two curves along two lines. Recall that it is along 30 and also along the 80. First, the first method involves the drawing two rectangles. Okay, two rectangles. So I'm going to enter 0, 100, 100, and 0. Okay. Basically, you need to define this rectangular coordinate. Okay, rectangular coordinate. And it is defined in this way. So you have your x. So the rectangle has 4 vertices. So the x will have 4 entries. And the y will also have 4 entries. And z will also have 4 entries. So the first point is 0, 30, and 0. So the first vertex coordinate will be at this location. So that is x is 0, y is 30, and z is 0. Okay, so that is the first location, first point here. Second location will be this 100. So x is 100, y is 30, and z will be 0. Okay. Basically, each column 0, 30, 0 is the coordinate of 1 point. Then the third value, third coordinate will be x will be 100. Okay, x will be 100. So y will also be 30. Z will be the height. Here you'll see that the height is between 0 and 0.05. So we are going to estimate this value will be about 0.025. Then we enter 0.03 will be high enough. Okay. The last point will be this location, that is x is 0, y is again 30, because this entire plane will be parallel to the y is equal to 30. Z will be 0. Okay. So we have defined the coordinate. We use the patch command, x, y, z, to draw a rectangle. And the color is magenta. Okay. We want to make it to be somehow transparent a little bit. So we set the face alpha to be 0.08. Okay. You can adjust this value. Okay. There will be no edge. Otherwise, you will have a black edge, which looks not very beautiful. No. Okay. Then okay. Problem here. Here's 3. Okay. Okay. Okay, better. So here we draw a plane that intersects this y is equal to 30. Okay, y is equal to 30. So this intersection, this two plane intersection will be this flux curve. Okay, flux curve. Then we will draw another plane at y is equal to 80. Okay, y is equal to 80 now. So the z will be taller, because at the 80, you see the z will the neutron flux height is higher. So we will set as the z to be taller. Okay. Now we will patch again. Now will be taller. Otherwise, it will not cover the entire height. Okay, we will reuse this x location, because x location is not changed. Okay, we have another. We will have another plane that will intersect this the other part. Okay, so this will be the solution. This is method 1. Okay, we can also change the title. Okay, change the title so that it will contain the K. Just copy this part here. Okay, now K is equal to this one. Now let's do a method number 2 for the plot. I'm going to get a new figure. Okay. Get a new figure so that I'm no longer plot the previous figure. So here we are going to use our traditional try to grade. First, I'm going to get a series of x between 0 and 100. Okay. Then I'm going to interpolate the neutron flux at 30, at y is equal to 30. Try to grade PTU, P, T, and U. Pay attention that now you see the U is a matrix. It is number of nodes by 33 number of eigenvalues. Only the first eigenvalue is useful to us. Therefore, we will choose the first set of the solution. Okay, so the first eigenvalue associated neutron flux. Okay, then we have our x. So y will be 30. Okay, y will be 30 because we interpolated this one along the y is equal to 30. We want to find those values. Pay attention that our u, we double click the u. You see that the first column, everything is negative. Okay, everything is negative. Therefore, we should manually make it positive. So I'm going to put a negative sign there. If your result is already positive, then you don't have to put this negative sign here. This is 80. This is 80. Okay. Next, we do a plot. Okay. We can put the figure later. Put a figure here. But it doesn't matter. We'll plot x versus y30. Then same x versus y80. Okay. We want to make this figure beautiful. So I'm going to change the first one to be red. First one is red. Second one is blue. Okay. And first one is solid line. Second one is solid and dashed line. Okay. It's a good habit to change the line style so that when you print your figure black and white, the reader can still differentiate those two lines. If everything is solid, then those color on black and white printer will not be shown. Again, we have our x label. That is x, unit is centimeter. Y label will be neutron flux. We turn on the grid. We have two lines. You need to have the legend. so that the reader will know which one is which. For the legend, we have two lines. So the first one is Y neutron flux. We can say it is flux or neutron flux, or just the Y is equal to 30 centimeter. Okay. Make it short, so it will not cover too much of the space. 80 centimeter. Okay. We should have the same title. Okay. So we know the K. How much is the K? All right, we have everything written here. We plot it. Okay. So this will be the second method. So you see that we have our y equal to 30, okay, which is this line, okay, this line. And this blue line is y is equal to 80, which is the taller one. Okay. So here we have shown two methods that will give you the plot. You can pick the one you like. Okay. So this will conclude this demonstration. Thank you. Now we have already solved the problem. Before I go to the plotting or the post-processing, I'm going to use the slides to summarize what we have done. First, you need to choose the generic scalar. Okay, generic scalar. This will define the type of the problem the toolbox is going to solve. Then you need to draw the geometry precisely. Okay, from 0 to 100 for the x, 0 to 100 for the y. And you have core 1, core 2, and also the reflector. When you are assigning the PDE coefficient, you need to follow the equation we have previously determined. So the C is the D, A is the sigma A, D is the mu sigma F. For example, for core 1, that is shown in the lower left figure, you need to choose the eigenmode. So it is eigenvalue problem. And you see that the C is the D, that is core region 1 D. A is the sigma A, that is core region 2, core region 1 sigma A, 0.12. And the D is mu sigma F, and for core region 1, that value is 0.1825. And you repeat this process for the core 2 coefficient and also the reflector coefficient. Okay. Next, in the boundary condition mode, when you are setting the mirror boundary condition, which is the left and the bottom boundary, you need to choose the Newman and set both G and Q to be 0. So that is the determined value for the mirror boundary condition. For the vacuum boundary condition, we are going to set the vacuum boundary condition to top and right boundaries. For the vacuum boundary condition, we set the G to be 0 and Q to be 0.46922. Okay, that is the boundary condition. Next is the mesh. And I would recommend you use the mesh parameters. Set this maximum edge size to a value, then generate this mesh using one step to get a relatively higher quality of the meshes. Next, you must adjust the eigenvalue search range. Do not use the default one, otherwise your calculation will go forever. So theoretically, there are many numbers, there are many eigenvalues inside this system, and the number of eigenvalues is equal to the number of unknowns, number of nodes. So there are many eigenvalues. And for each eigenvalue, there is a set of eigenvectors, which is neutron flux in this scenario. For our neutronics problem, we just need the largest k. Okay, among all those eigenvalues, among all those k you find, we need the largest one. We also know that in MATLAB, the lambda is called the eigenvalue. So lambda is equal to 1 over k. If we want to find the largest k, we need to find the lowest lambda. Okay, the smallest lambda will give us the largest k. Okay. So the strategy is that we are going to search the eigenvalue within 0 and 1, or within 0 and 2. In most of the cases, 0 and 2, between 0 and 2, you will find your solution for sure. If not, either the problem is very strange or something wrong in your setting. So as a rule of thumb, you may try to use 0 and 1 first. If there's no eigenvalue found, then you set this search range to 0 and 2 and calculate again. If nothing show up, then further enlarge this range. Okay. For this case, we try 0 and 1 first. If you find this k within, you find this lambda within 0 and 1, you will get a k that is higher than 1. So your reactor is supercritical. Then if there's no solution between 0 and 1, and you get your lambda larger than 1, and your reactor, your k, will be smaller than 1, and your reactor will be subcritical. Next is the comments for the plot. We are solving an eigenvalue problem. So in the plot selection dialog, you will see that there's a location that will allow you to choose different eigenvalue. So it means that you can plot the solution for different eigenvalues. Each eigenvalue will have its own solution. By default, the smallest eigenvalue is already selected for you. So that is the one we are going to use. And the other eigenvalue will not be used. So those will be the trivial solution, and we are going to disregard that. Another thing is that occasionally you will see that your solution are negative. So in realistic, the neutron flux cannot be negative. So there will be there should be positive neutron flux. The reason is that this neutron flux phi appear in every terms inside this neutron diffusion equation. Means that if this phi is the solution to the system, the negative phi is also the solution of the system. So it means that it is possible for the solver to give you a negative solution. Then that solution is correct. The only thing we need to do is to multiply -1 to this solution, and that is your all positive solution. Therefore, when you are doing your plot and you see that the solution is negative, do not panic. Just inside this property, instead of plot the u, you are going to choose the user entry. Then in the user entry, you enter -u. Then everything will be positive. If your solution are already all positive, then you don't have to change anything here. After those adjustments, we have the neutron flux distribution, and also our lambda, as shown here, that is 0.66841. Remember that the lambda is not the k. We have to manually calculate the k, because in nuclear engineering, the k is defined as 1 over lambda. Okay. And we simply calculate the k as 1 over lambda, and that is 1.49609. Okay. Next, we are going to do some post-processing. We need to export the solution and the mesh information to the workspace. Because this is the eigenvalue problem, when you export the solution, you will see that you have two variables. One is the U, another one is the L. The U is the neutron flux on each node. The L is the eigenvalues. Okay. So this vector L contains all the eigenvalues found in your search range. Only the L1 is meaningful to us, because L1 is the smallest lambda, and all other values are trivial solution we do not use. In this case, the calculation found 33 eigenvalues. The first one is useful, the other 32 are not useful. Okay. The matrix U contains the eigenvectors. In this case, it is called neutron flux on each node. You see that this U is 4390 by 33. So the dimension is 4390 by 33. So we have 4390 nodes, which match the P. And it also have 33 columns. So each column corresponds to each eigenvalue, to one eigenvalue. So we have 33 eigenvalues, so we have 33 columns inside this U. And only the first column of this U is useful to us, and all other columns are trivial solution. Okay. So we display this K. Simply K display the K is equal to number to string 1 over L1. Okay, only the first eigenvalue is used here. So the K is equal to 1.4961. Next, we did some plot. I demonstrated two methods to show the flux curve along two lines. Okay, the first one is to draw two rectangles and intersect these two rectangles with our neutron flux distribution. And basically, we use the patch command to draw this rectangle in 3D space. And those rectangles are placed into the figure that was created by the MATLAB PDE modeler. Again, you should have your X and Y label and unit if they are applicable. And also the Z will be neutron flux. In this case, the neutron flux has no unit because the flux solution only represents the relative magnitude. Because if the phi is solution, then we multiply this phi by another scalar value, then a phi is also the solution. So different students may get different result, and your values, neutron flux value, may be different. However, the flux shape and the eigenvalue should be the same. The second method use our previous method. So we use the try to grade to get the neutron flux solution at different location. And pay attention that here, when you are interpolating your value, you are going to use the U column 1. Means that we are going to select the first set of the eigenvector, first set of eigenvector, and plot them together. So this will conclude our demonstration for the one group, two-dimensional neutron diffusion equation solved by the MATLAB PDE toolbox.